Hello and welcome back to Counting Rocks, an introduction to combinatorics at CSU. Today we'll be talking about set partitions, which is another construction in set theory that we're going to need for a number of different combinatorial applications. In particular, in the last video, we saw how sets can help us express the addition, multiplication principle, and subtraction principles on a more rigorous foundation. And now we're going to be looking into the division principle, as well as a number of other applications of set partitions. So what is a set partition? A set partition of a set S is a set of disjoint subsets of S whose union is S. So here's an example of a set partition. The entire set S here is the set containing 1, 2, 3, 4, 6, and 7. And the set partition we've created here is a set of three subsets, 2, 3, 7, 1, and 4, 6. These subsets don't have to be the same sizes, but they do have to be disjoint. None of the two sets overlap. We draw them as disjoint circles that don't have any intersection. They also have to be non-empty. We don't allow the empty set as a block in our set partition. So these little circles are called blocks, and so this is a set partition with 3 blocks. So let's see if we can write down all the set partitions of small sets. What are all the set partitions of the set containing 1? Well, in this case, there's only one way to make a block, the block containing 1 and nothing else. For 2 elements, it gets a little more interesting. We can either have 1 and 2 both in the same block, or 1 in its own block and 2 in a separate block. For 3, it gets a lot more interesting. You can have all 3 elements in one block, or you can have 2 elements in one block and 1 element in another block in 3 different ways, because that block with 1 element can either have 1, 2, or 3 in it. And finally, you can have all blocks of size 1, and there's only one way to do that, because again, this is a set of subsets, and so the order of the blocks doesn't matter. Now, the Bell numbers are a famous sequence in mathematics that count the number of set partitions of 1 through n. They do have some nice formulas that we may get into later in the course, and for now, we've just calculated the first 3 Bell numbers. There's one set partition of 1, so b of 1 equals 1. b of 2 is 2, because there are 2 set partitions of 2. And there are 5 set partitions of 1, 2, and 3, so b of 3 equals 5. So the first 3 Bell numbers are 1, 2, and 5, and it's a very nice sequence in general. Now let's revisit the division principle from the perspective of set theory. So the setup is you have a set S with a set partition P having k blocks of equal size B. So in general, set partitions don't have to all have the same size blocks, but for the division principle, the setup is that we have all 3 subsets here of size 2 in this example. And so this picture demonstrates either the fact that 6 divided by 3 equals 2, because if you sort 6 things into 3 equal size groups, you have 2 in each block. And it also demonstrates that 6 divided by 2 equals 3, because the other division principle says that if you have 6 things and you divide them into groups of 2, how many groups are there? 6 divided by 2. So that captures the 2 division principles that we talked about in the language of set theory. Now let's look at one of the most famous set partitions in mathematics. The set partition of z by taking mod 2. Mod means the remainder when you divide by 2. So every number either has a remainder of 0 or 1 when you divide by 2. In particular, it's either even or odd. So we call even the set of even numbers, and odd the set of odd numbers, and these are what we call 0 and 1 mod 2. This forms a set partition of the entire integers, and this is an example of a set partition of an infinite set. We use 2 infinite subsets, and they are disjoint, and their union is all of the integers. You can similarly set partition Z into 3 blocks by taking the numbers mod 3. Here's all the numbers with a remainder of 0 mod 3, negative 6, negative 3, 0, 3, 6, etc., all the multiples of 3. Then you put all the numbers that are 1 mod 3, that have a remainder of 1 when you divide them by 3, in another block, and finally all the things with a remainder of 2 when you divide them by 3 in a third block. And so we can, for shorthand, write this as the set of remainders 0, 1, and 2 taken mod 3. So let's define this mod term. The quantity a mod b is the remainder when a is divided by b. So that's one way of writing down mod as a binary operation. 17 mod 4 is 1, because when you divide 17 by 4, you get 4 with a remainder of 1, and so the remainder is the answer. But there's another way we use this mod notation. We say 2 numbers a and c are equivalent mod b if a mod b equals c mod b. So if a and c have the same remainder when you divide them by b, we write a is equivalent to c with 3 lines for our equivalence sign. And then we put mod b in parentheses on the right, just to tell us that we're thinking mod b when we think of this equivalence. We're not thinking mod d or some other number. So here's an example. 17 is congruent to 41 mod 4 because when you divide 17 by 4, you get a remainder of 1. And when you divide 41 by 4 you get a remainder of 1, so they have the same remainder, mod 4, and so they are congruent mod 4. Now, we're going to use a lot of properties of mod, and here's some of the most important ones. First, it's an equivalence relation. That means it's reflexive, so anything is congruent to itself, mod b, for any fixed b. It's symmetric. If a is congruent to c mod b, then c is congruent to a mod b, because they have the same remainder. And it's transitive. If a is congruent to c mod b, and c is congruent to d mod b, then a is congruent to d mod b. These are three properties of equality, and congruence mod something satisfies these same three properties. But the more important properties are the arithmetic properties of modular arithmetic. One is addition. So a plus c is the same as a mod b plus c mod b mod b. This is a mouthful way of saying that if you want to know the remainder when a plus c is divided by b, then you can first take the remainder when a is divided by b, and take the remainder when c is divided by b, and add those remainders together. You might have to take that mod b again, but it's a shortcut. You can simplify the two terms mod b before you add them, and that saves a lot of work. Same for multiplication. A times c is the same as a mod b times c mod b, taken mod b. So here's an example in practice if we want to find the remainder of 203 times 19 when you divide it by 4. You don't want to take 203 times 19, expand that all out, divide it all by 4, and find the remainder. Instead, we can take the remainder when 203 is divided by 4, which, since 4 goes into 200 evenly, the remainder is 3. And the remainder when 19 is divided by 4 is also 3, so we can just do 3 times 3 instead. That's 9, which has a remainder of 1 when you divide it by 4, and so the total answer is 1. You can check this. If you take 203 times 19 and you divide it by 4, you're going to have a remainder of 1. So let's look at a fun application of modular arithmetic in combinatorics. Say today is Sunday. What day of the week will it be 2 to the 100th days from today? So when we're talking about days of the week, we want to use modular arithmetic because weeks have 7 days in them. So whenever you go 7 days forward, you come back to the same day. So 7 days from now it'll be Sunday, 14 days from now it'll be Sunday, and so on. So we want to take 2 to the 100th and divide it by 7 and see what the remainder is. The remainder will tell me how many days forward we walk in the week from Sunday. So we want to calculate 2 to the 100th mod 7. To simplify this, we look at patterns of powers of 2 when we take the remainder mod 7, and we find that 2 is 2 mod 7, 4 is 4 mod 7, and 8 is 1 mod 7. 8 has a remainder of 1. And that's great because we can take all the 2 to the thirds and replace them with 1 in our calculation. So 2 to the 100th can be written as 2 to the third to the 33rd power. I'm basically writing this as 2 to the 100th is 2 to the 99 times 2. So it's 2 to the third to the 33rd times 2, and 2 to the third is 1. So when we multiply all those 2 to the thirds together, we might as well multiply all these 1s together. We can replace the 2 to the third with the 1, and so now we just have 1 times 2, because 1 to the 33rd power is just 1, and so that's 2. So the remainder when 2 to the 100th is divided by 7 is just 2. And so what's 2 days from Sunday? Tuesday. So now let's look at equivalence relations in general, which actually correspond to set partitions. So an equivalence relation, say sim, on a set S, is a relation on pairs of elements that satisfies the reflexive, symmetric, and transitive properties that modular arithmetic does. So x is equivalent to x for any x. If x is equivalent to y, then y is equivalent to x. And if x is equivalent to y and y is equivalent to z, then x is equivalent to z. Those are the three properties of equality, and they're the three properties that define an equivalence relation in general. For instance, equals is an equivalence relation on any set. Congruence mod 7, or mod anything, is an equivalence relation. And also things like graph isomorphism. Notions of when two mathematical objects are the same is usually an equivalence relation. So once you have an equivalence relation, it's nice to define equivalence classes. The equivalence class of an element x of a set that you have an equivalence relation on is the set of all y in that set that are equivalent to x. So the equivalence class of a set of an element x is the set of all things that are equivalent to it. And the fact that we need is that equivalence classes always form a set partition of S. We saw this with mod when we saw, well, mod is an equivalence relation, and the equivalence classes for, say, mod 2 were the evens and the odds. The equivalence classes mod 3 were 0 mod 3, 1 mod 3, and 2 mod. Let's look at equivalence relations and set partitions in a combinatorial example. Let's let S be the set of all ways of labeling the 6 beads on the circle, as shown here with 1 through 6. and make an equivalence relation of rotation equivalence. So remember the necklace problem where we say, okay, in the division principle, we're going to assume that necklaces are equivalent up to rotation. Well, what you can do is overcount by overcounting all the necklaces, and then divide by 6 because there's 6 ways to rotate a necklace. Well, here we're putting this on a formal, rigorous foundation by saying we're defining the equivalence relation between two necklaces to say two necklaces are equivalent if you can rotate one to get to the other. For instance, this one is equivalent to the next one because you can rotate it just one step to the right and you get the next necklace. So there are 6 things in the equivalence class of any given element. And so we have a set partition then of the equivalence classes under necklace rotation, and each equivalence class has 6 elements. So here's where we can use the division principle. Since every equivalence class has the same size, we can take all 6 factorial ways of labeling the 6 boxes with 1 through 6 and divide it by 6 to get the number of equivalence classes. And the equivalence classes correspond to the necklaces up to rotation. So there are 120 necklaces up to rotation. Again, different language for saying the same thing as the necklace problem we've already done in a previous video. And now you try, how many set partitions are there of the set 1, 2, 3, 4? So in other words, what's the Bell number B of 4? We calculated B of 1, B of 2, and B of 3, and now it's your turn to calculate B of 4. That's all for today, and I'll see you next time.